So let's say someone actually asks you to solve a logistic differential equation. So our first step would be to separate the variables. And one thing I always do is I don't really like having the fractions, so I could multiply both sides by the 6,000. Now I know to separate, the dt has to be in the numerator, so I am going to multiply by the dt. So just to start with, what that looks like is a 6,000 dp equals 18,000 p minus p squared dt. And the variables are not separated yet. So what I have to do here is get all of my p's to the left-hand side. So I'm going to say that this is 6,000 over 18,000 p minus p squared dp equals dt. And there are different ways to do this. Some people leave the 6,000 on one side, etc. But we have separated the variables. Everything's going on with my population. I have this only little dt out here. But I'm going to integrate both sides. So the right-hand side is easy. I know that this is going to equal a t plus some c. On the left-hand side, I have a lot more work to do. And if you start looking at it, you want it to be u sub, but it isn't because of this p squared, and there's no p up here. So it's not u sub, but I have a fraction. So this is most likely a partial fractions problem. So what I'm going to do is factor the denominator. So I'm going to pull a p out. So this is the integral of 6,000 over p times 18,000 minus p. So I have, and this is dp. So I have two factors in the denominator. So what I'm going to do is actually do this with Heaviside method with partial fractions. And I'm going to say that I have some a value over p for my first one plus some b value over 18,000 minus p. And I'm going to figure out what that is, what my a and my b are to split this up. So I know that it's a times 18,000 minus p plus b times p has to equal 6,000. This would be the numerator if I actually got the common denominator. So the a gets multiplied by this, the b gets multiplied by that, because these are multiplied, and that has to equal 6,000. So I pick two different populations that will make each one of these go to 0. So if I pick p equaling 18,000, 18,000 minus 18,000 goes to 0. That cancels out my a, and I'm left with 18,000 times b equals 6,000. So I know that my b equals 6,000 over 18,000, or 1/3. The next value I'd pick is 0, because that will make this term go to 0, so p equals 0. And that means I have 18,000 minus 0, which is 18,000 times a, equals, this is 0, 6,000. So divide both sides by 18,000, and a also equals 1/3. So no, I know that I'm actually integrating 1/3 over my population and 1/3 over 18,000 minus my population, so it looks like this. And I can pull the 1/3 out, leave it in the numerator, whatever I want to do. I'm going to pull the 1/3 out here. Actually, I'll leave it on top just because it looks like other problems that we've done. We're integrating this with respect to p, and I know that still equals t plus c because I integrated the right-hand side. Okay, this is logarithmic. So I have my p in the denominator, it's p to the negative 1, so this will be 1/3 the natural log, the absolute value of my p. And then I look at this, I'm going to have another 1/3, but this one is u substitution. It's also logarithmic, but it is u sub. So u would equal 18,000 minus p, so my du would be a negative 1. So I need to pull a negative out. And then it's the natural log of 18,000 minus p equals t plus c. So I'm closer. My goal, of course, is to get solved for population. I'm trying to solve the differential equation. One thing I can see I can do, because I've got logarithms and these are both to the 1/3 power, I can raise the 1/3 up, or I could just really go through and multiply by a 3 right now, and that makes it nicer. So I'm going to say the natural log, the absolute value of p, minus the natural log of 18,000 minus p equals 3t plus c. Properties of logs, I have subtraction right here. I know subtraction goes with division. So this is the natural log of, we have a p over an 18,000 minus p equals 3t plus c. And I'm narrowing in on it. So I'm going to rewrite that. We have the natural log of p over 18,000 minus p, the absolute value, equals 3t plus c. My next step is to get the natural log off. So I'm actually changed this from logarithmic form to exponential form. ln is base e. So I know I have e to the 3t plus c equals the absolute value of p over 18,000 minus p. And again, I'm getting closer. I need to get rid of the absolute value, and I can actually take care of it with this c right here. So I can let k equal plus or minus e to the c. And just a reminder that if I want to split this up, this is really e to the 3t times e to the c. Because when I multiply two things with the same base, I add the exponent. So I can undo that. Now what I'm doing is I'm going to say that e to the c is k, but I'm going to make it positive or negative, and that lets me remove the absolute value. So I have k e to the 3t equals p over 18,000 minus p. Now again, I actually want to solve for p, so I need to get down to 1p. So what I'm going to do is take this 18,000 minus p, and I'm going to multiply it up into the numerator. So I have k e to the 3t times 18,000 minus p equals p. I'm going to distribute. So I have k e to the 3t times 18,000 minus p k e to the 3t equals p. And what all of this allows me to do is actually get my p's together on one side so I can factor it out. So I'm going to add this to both sides. So I have 18,000 k e to the 3t equals p plus p k e to the 3t. Now you can see that while I still have two p's, they're on the same side, they're both in the numerator, I can factor my p out. I'm left with 1 plus k e to the 3t, and then over here I still have my 18,000 k e to the 3t. So to solve for p, I'm going to very simply divide by this on both sides. So I'm going to write it with p on the left equals 18,000 k e to the 3t over 1 plus k e to the 3t. And that is the logistic differential equation solved for p. Now if I actually went to solve for the k, you would have to be given a starting population. So let's go ahead and do that, and I could have plugged it, if I'd known it, I could have plugged it in sooner and solved sooner, but let's just say we didn't. So we know at the population at time 0 equals 1,000. Then if I need to solve for k, I'm going to go ahead and put this in for my population. So I would say 1,000 equals, and then the 0 goes into my t, so 18,000 k e to the 3 times 0 over 1 plus k e to the 3 times 0. 3 times 0 is 0, and I know that e to the 0 is 1, so that's 1 and this is 1. So now if you look at the equation that's left, we're trying to solve for k, and I have k's in both numerator and denominator, so I'm going to go through the same process I did up here. I'm going to multiply both sides by the 1 plus k. So I have 1,000 times 1 plus k equals 18,000 k. I'm going to distribute my 1,000 equals 18,000 k. Subtract 1,000 k from both sides, so I have 1,000 equals, let's see, it's 18,000 minus 1,000, 17,000 k. Divide both sides by 17,000, and k equals 1,000 over 17,000 is 1/17. So I could go back into this and I could put in a 1/17 right here and right here, and I would have a particular solution to the differential equation when the population starts at 10,000. This is the general solution, and then if I actually solve out for my k, I have the particular solution, and that is solving one logistic problem.